Welcome to the Tech and Space Leaders Show, where we learn lessons from leaders of the next frontier. I am your host, Lisa Dreher, and I am very excited to introduce our guest for today, Pat Haddox. He is the CEO and co-founder of Samara Aerospace. Welcome to the show, Pat.
Thank you so much for having me. Appreciate it.
Absolutely. Thank you for making time to be here. Maybe we can start by having you give a little bit of background on yourself and Samara Aerospace.
Prior to Samara, I was an aerospace engineer by trade. Spent time in everything from software, working on orbital trajectory optimization, to ground systems, to satellite hardware itself. Always had a specialty sort of in satellite dynamics, how they move, how they rotate. And Samara kind of spun out of that. So a good friend of mine, Vedant, from the University of Illinois, I got to watch him invent a new way to rotate satellites in space. And we both sort of collectively saw the potential that could have on the industry in terms of completely changing how you go about designing satellites for the better. So we decided to build a company around it to create the next generation of satellites.
Wow, amazing. So why do we actually need to change the way that satellites are designed and deployed?
I would say due to stagnation of satellite designs. It annoys me and Vedant that satellites haven't really changed much in our lifetimes. The payloads get more advanced and complex, but the satellite bus, the vehicle that supports the payload, all the life support, it kind of looks the same as it did 30 years ago. So we like to draw the comparison to the current evolution to electric cars. Throw out all the, environmental concerns, the emissions, all that. What I see in an electric car is this evolution from this clunky thing where you have an exploding gas engine and an alternator and a torque converter and a transmission, catalytic converter, a muffler, all of these parts that are really just there to apologize for this exploding engine. Then you have an electric car, no more none of those external, parts. It's just a battery and a motor. No more oil changes. It's more efficient. They're the fastest cars on the road. So that's what we want to do to satellites. We want to eliminate unnecessary problematic parts and improve the performance and the efficiency. And we do that through our new MSAC technology, which I'm happy to dig into a little bit.
Yeah, let's definitely get to that. So, what are some of the biggest challenges that are faced with traditional satellites, the deployment of those traditional satellites?
So I guess you could interpret that a couple of ways. The challenges with deployment, I would say, is the challenge of getting your thing into space. And I would say that boils down to two things, which would be supply chain and our launch infrastructure. So with traditional satellites, there are supply chain bottlenecks, both in terms of the reaction wheel system, which is something that we are trying to replace. Only a handful of manufacturers exist that sell those components. And then solar panels, if you want to fly, triple junction solar cells to get the most efficiency out of your system. Those have an extremely long lead time. And those two are two of the most expensive things that go into a satellite, which is why we're targeting them. So with us, we can eliminate the wheels and also enable much larger solar panels through our control technology, which makes the switch from triple junction, long lead time cells to very common silicon cells, which have less efficiency, all the easier, I guess.
Got it. Okay, so are there other things that Samara is doing differently from a traditional satellite?
No, I think from our customers' perspective, we're going to show up just exactly the same way as any other satellite bus manufacturer. It should be plug and play, should be seamless. You're going to communicate with us in all the same ways. It's just that our bus is going to be slimmer, lighter, and solve a lot of the problems that the industry sees, which would be jitter, flutter, challenges with scaling, stuff like that. So we have a lot of unique benefits involved in our satellite that I think our customers are going to love.
Great, great, great. So let's jump into that MSAC. So you'll have to define that for us and talk a little bit about its capabilities.
Yeah, happy to, because this is where we lose a lot of people, especially engineers. They, think we're blowing smoke here, but MSAC stands for Multifunctional Structures for Attitude Control. I promise we're working on a better name for that, but in the meantime, we'll call it what it's known as, at least by the patent department. So it is patented technology developed at the University of Illinois. Basically, all we do is we put actuation directly into the hinges of our deployable solar panels. And what this allows us to do is very, very slightly pitch the panels up and down and left and right. And when you're clever about how you actuate these hinges, you can actually vibrate little circular patterns right into the solar panels. And when you vibrate a mass in a circle, you get the exact same physical effect as spinning a wheel in a circle. So you fully replace these wheel-based systems that everyone else is flying as another component, and you're sort of getting dual use out of the solar panels by storing, if you want to get a little technical here, we're literally storing angular momentum in the panels themselves in the form of a vibration right around the resonance frequency of the panel material. But that sounds a little clunky. So what we do is we layer on top of that active noise cancellation, exactly like a pair of noise canceling headphones. We're always listening right at the center of our satellite bus to vibrations at a very high rate. And we're just doing an equal and opposite bump with the solar panels to make sure that any payload flying at the center gets about 1,000 times reduced jitter and noise as compared to a spinning wheel right next to it.
Wow, that is amazing. Okay, so that's really, really interesting. Where is Samara in terms of your development process right now?
Yeah, so we're still pretty early. Just closed out a pre-seed round, have some government dollars in the door in the form of phase 2 SBIRs and whatnot. We're pushing towards flying our first prototype. So we're actually delivering next month a set of 4 MSAC flexures with a dummy mass on it. So that'll fly as a hosted payload in October on the Transporter, I think, 15 mission. So that'll allow us to show 3-axis attitude control at a very small scale, and also just sort of give us additional flight heritage on the system. Right now, it's been validated in the lab, and 1 axis at a time, little spin tests and whatnot. Yeah. And then we're also working on a Hummingbird satellite mock-up in our lab. That's hanging by a crane right now, and it's capable of doing little slew maneuvers in the lab, but we're flying that on a 0G parabolic flight known as the Vomit Comet in November. So we'll be up there with it, doing 3-axis attitude control, noise cancellation, panel deployment, all that fun stuff.
Wow, that is really exciting. So really you're on the cusp of starting some of these test flights. That's really great. When you look at this particular satellite design, are there specific use cases that it might be better suited for, or is it something that can be used for sort of any sort of payload and mission?
Yeah, it's kind of both. We're designing it, again, to be fully generic. I think no matter what you're flying, you're going to see a benefit in terms of, mass and volume efficiency, having a smaller footprint in the launch vehicle, which enables you to either increase the size of your payload or just save on launch costs. But I think the sort of beachhead market that we like to target are people who are struggling with these very real problems that we solve, mainly in the form of jitter. So think anybody with a sensitive optic payload. If you're trying to take a picture of the Earth or pointed the other direction looking at stars, if you're NASA, if you are trying to set up a communication network of laser-linked satellites like Starlink, OneWeb, Project Kuiper, all these people. They all battle jitter every day. It's a problem that most of the industry has just accepted as a fate, and they have to work around it. And you just can't. You have no control. You have to fly these spinning wheels that cause jitter on your satellite, and you have to work around it. So we are offering an alternative, and instead of adding jitter to the system, we are actively removing it from the system. So those are the people who are going to see the immediate benefit. But then anyone trying to scale satellites to create ultra large platforms with very large solar arrays, that is a huge use case for us. And I don't know if I mentioned before, we are uniquely capable of scaling power and agility in the same direction, which is one of our biggest selling points. So everyone else, as you create a very large solar array, you're also creating a big flimsy structure that's very difficult to rotate, and then it also flutters after every maneuver. With us, it remains perfectly steady because it's actively damped, and then we actually add control to the system with every panel, so you can maintain your ability to quickly rotate in space.
Fascinating. So what are some of the biggest challenges that jitter kind of pose for these satellites?
Yeah, so Earth observation, for example, it's just going to blur your imagery. It's going to make it more difficult to get high resolution photos. And a friend of mine at another company who works on optical laser links, I like to quote him because he said, laser communications are not an optics problem, they are a pointing problem. And that is extremely, like when you're trying to point a laser from one satellite to another satellite and close basically an internet link, that is extremely difficult if you're shaking and that laser is sort of bouncing all over the place.
Yeah.
So that's sort of the potential here, is we can bring that noise down and allow you to remain perfectly steady as you try to do these sensitive operations.
Got it. Okay. So how big are these satellites?
They scale very well. So right now we are baselining two forms of our Hummingbird satellite bus. One will be 500 kilograms and below. That's kind of standard for this new class of sort of mega constellations going up right now. And then we have a larger form factor, which we're calling the Kite, and that will go up to about 2,000 kilograms. So they can be quite large, but we make them fully modular. So depending on customer needs, if you don't need a lot of power, you can just put 2 panel segments on it. If you need a lot of power, put 8 on there. You don't have to worry about additional flutter, jitter, control issues. That's just sort of inherently solved by our system.
Oh, wow, fascinating. Okay, so in terms of growth in this market, where do you see the major growth opportunities from a satellite perspective over the next decade?
Yeah, I think the easy answer is the fact that more than half of all satellites in orbit right now are Starlink space-based internet satellites. And while they have sort of market dominance, there are going to be sovereign nations that are not the US that want to fly their own constellation for security reasons, or their other competitors just want to enter the market. So I think that's not going anywhere anytime soon. So I think that's an area for growth. And then, unfortunately, what you're seeing is a lot of posturing by different nations right now in space, and there's sort of a contested space environment, and I think defense use cases are going to scale up. And then while you have thousands and thousands of satellites going up, more traffic means more traffic cops, and I think there's going to be a lot of space situational awareness satellites, people kind of monitoring and looking at other satellites in orbit, making sure they are what we think they are, et cetera. So I think there's going to be a lot of growth built on other growth.
Sure. Sure, sure. Well, thank you so much for making time to be here today. If someone wanted to learn more about Samara Aerospace, what should they do?
Yeah, they can go to samaraAerospace.com. We're working on a new website at the moment, but they can also email us through the contact form on the website. And feel free to ping me on LinkedIn too.
Excellent. Well, thank you so much for making time to be here with us today, Pat. We really appreciate it.
I'm stoked to be here. Thank you so much, Lisa.
Absolutely. And I do want to take a moment to thank GuideForce for hosting these sessions. To learn more about GuideForce, you can visit guideforce.com. And we'll see you next time on the Tech and Space Leaders Show.